Your starship is holding steady at what your instruments say is a safe distance. The black hole is still millions of miles away. You have not crossed the event horizon. You are not even close, but something is already wrong. The hull temperature is climbing. Your navigation system cannot agree on which direction is forward. The clocks in the engine room and the clocks on the bridge are no longer synchronized. And the force pulling on the bow of your ship is measurably stronger than the force pulling on the stern. You check your fuel, you calculate the burn needed to turn around, and that is the moment you realize the truth. You're not about to be swallowed. You're already being taken apart, and the event horizon is still impossibly far away. If you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, brace yourself. Let's begin. Picture a starship. Not a fantasy vessel from a movie with shields that absorb anything the universe throws at it. A real machine built from real materials by real engineers working within real physics. It has a hull forged from the strongest alloys available. It carries radiation shielding designed to protect its crew against the worst conditions interstellar space can offer. Its navigation systems are precise enough to plot a course across light years of emptiness and arrive within a margin of a few thousand kilometers. Its engines are powerful. Its fuel reserves are calculated for the mission and the return. And that mission is straightforward. Approach a black hole. Get close enough to study it directly. Gather data that no telescope could ever collect from a safer distance. And then come home. The crew understands the basic rule. Stay away from the event horizon. Do not cross the point of no return. Keep a safe margin, collect the data, fire the engines, and fly out the way you came in. That is the assumption. That is what every pre-mission simulation predicted. And that assumption is catastrophically wrong. Not because the event horizon is harmless, but because treating it as the single line between safety and death ignores everything that happens before you reach it. The event horizon is not where the danger starts. It is where the danger ends. By the time anything arrives at the event horizon, the story is already over. The destruction, the radiation, the impossible forces, the total loss of every possible escape path, all of it happens earlier. It happens outside the black hole. And it happens in stages, each one more severe than the last. Each one closing a door that the crew did not realize was still open. To understand why approach alone can become a death sentence, you have to understand what a black hole actually is. Not the swirling purple vortex from a movie poster. Not a hole in space that sucks everything toward it like a drain. The real thing. And the real thing is simpler and more terrifying than any film has ever managed to show. A black hole is what remains when gravity wins completely. Every star in the universe exists in a state of tension. The outward pressure of nuclear fusion in its core pushes against the inward pull of its own gravity. For most of a star's life, those two forces balance. The star holds its shape. It burns steadily. It fills a volume of space proportional to its mass. But when the fuel runs out and the fusion furnace dies, the outward pressure vanishes. Gravity, which has been waiting patiently for billions of years, is suddenly unopposed. And if the star is massive enough, roughly 25 times the mass of our sun or more, nothing in the known laws of physics can stop what happens next. The core collapses, not slowly, not gently. The inner layers of the star fall inward at a significant fraction of the speed of light. In less than a second, a mass greater than our entire sun is compressed into a region so small that the concept of size begins to lose meaning. The matter does not settle into a new stable state. There is no new equilibrium. The collapse continues past every known threshold, past the density of an atomic nucleus, past any configuration where matter as we understand it can exist. What remains is a singularity, a point of functionally infinite density where the known laws of physics break down entirely. And surrounding that singularity, at a very specific distance, sits a boundary that defines the black hole itself. That boundary is the event horizon. Here is what the event horizon actually is. It is not a surface. You cannot touch it. You cannot see it. There is no wall, no membrane, no barrier. If you were falling toward a sufficiently massive black hole, you might cross the event horizon and not feel anything unusual at all in that exact instant. The event horizon is a mathematical boundary. It is the precise distance from the singularity at which the escape velocity, the speed an object would need to travel to break free of the gravitational pull, equals the speed of light. And because nothing in the universe can travel faster than light, anything that crosses this boundary is permanently trapped. It can never return. No signal, no particle, no piece of information can travel outward past that line. From the perspective of the rest of the universe, whatever crosses the event horizon ceases to exist in any meaningful, recoverable way. It is gone. The distance of the event horizon from the center of the black hole is called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who first calculated it in 1916, barely a year after Einstein published the equations of general relativity. The formula itself is deceptively simple. The Schwarzschild radius is proportional to the mass of the black hole. Double the mass and you double the radius, triple the mass and you triple it. The relationship is perfectly linear, and the numbers it produces are staggering in their compression. For a black hole with 10 times the mass of our sun, a typical stellar mass black hole, the kind formed from the death of a single massive star, the Schwarzschild radius is approximately 30 kilometers. That is smaller than a mid-sized city. All of that mass, 10 times the weight of the star that lights and warms this planet, crushed into a sphere roughly the diameter of a medium-length highway drive. For the supermassive black hole at the center of our galaxy, Sagittarius A star, with a mass of roughly 4 million suns, the Schwarzschild radius expands to approximately 12 million kilometers. That sounds enormous, and in human terms, it is, but compared to the astronomical scales of a galaxy, it is a pinprick. The entire event horizon of the most massive confirmed object at the heart of our Milky Way would fit comfortably inside the orbit of Mercury. Now, here is the critical detail that reshapes everything the crew of that starship thought they knew. The event horizon is not the outermost boundary of danger. It is the innermost. There are at least 3 distinct zones outside the event horizon where a spacecraft faces threats that can cripple or destroy it. The closest of these to the event horizon sits at exactly 1.5 times the Schwarzschild radius. It is called the photon sphere. The photon sphere is one of the strangest predictions of general relativity. It is the exact radius at which the curvature of space-time becomes so severe that light itself, photons, the fastest things in the universe, can be bent into a circular orbit around the black hole, not pulled in, not flung outward, locked into a loop. At this precise distance, a photon traveling perpendicular to the radial direction will circle the black hole indefinitely, tracing an orbit at the speed of light. Imagine turning on a flashlight while standing on the photon sphere. If you aim the beam along the direction of orbit, the light does not fly off into space. It curves around the black hole and eventually returns to the back of your own head. That is how warped the geometry of space has become at this distance. For a non-rotating black hole with a 10 solar mass core, the photon sphere sits at approximately 45 kilometers from the center. For Sagittarius A star, it sits at approximately 18 million kilometers. These numbers are not the event horizon, they are outside it, and yet the physics operating at the photon sphere already represents conditions that no spacecraft could survive under power. Here is why. The photon sphere marks a critical transition in orbital mechanics. Outside the photon sphere, the basic intuition of orbiting works the way you expect. Move faster and you feel a stronger outward centrifugal effect. Slow down and you begin to fall inward. It is the same logic that keeps satellites circling Earth. But at the photon sphere, that logic inverts. Centrifugal force drops to zero. Orbiting faster no longer pushes you outward, and inside the photon sphere, the reversal is complete. Accelerating actually increases the inward pull you feel. The faster you try to orbit, the heavier you become, the harder gravity drags you down. It is as though the rules of motion have flipped. A pilot trained on every principle of orbital mechanics would find that none of their instincts work inside the photon sphere. Speeding up does not save you. It condemns you. No circular orbit of any kind exists for a massive object at or below the photon sphere. Any spacecraft that enters this region on a roughly circular or slowly spiraling trajectory will be captured. There is no stable path to hold, no orbital speed that produces equilibrium. Even a high-energy flyby trajectory passing through this zone would require extreme precision to avoid capture, and any deviation from the exact required path ends in descent. An object inside the photon sphere can still escape, but only under continuous powered thrust directed radially outward, constant engine burn, fighting the curvature of space-time itself, consuming fuel at a rate that climbs exponentially the deeper you go. The photon sphere is not the point of no return for light, but it is the point of no return for anything relying on orbital motion alone. Now step outward. Above the photon sphere, farther from the event horizon, sits a second critical boundary. It has a technical name, the innermost stable circular orbit, and it represents the point at which even the concept of a stable orbit ceases to exist. In flat Newtonian space, you can orbit a massive object at any distance, provided you are moving at the correct speed. The closer you are, the faster you need to go, but in principle, there is always a stable circular path available. General relativity breaks this. Near a black hole, the curvature of spacetime introduces a correction to the orbital equations that creates an inner boundary. Below this boundary, no circular orbit is stable. Any object that drops beneath this radius will spiral inward toward the event horizon, unless it is under constant, active, powered thrust. There is no coasting. There is no parking. There is only descent. For a non-rotating black hole, the innermost stable circular orbit sits at exactly 3 times the Schwarzschild radius. For a 10 solar mass black hole, that is approximately 90 kilometers from the center. For Sagittarius A star, it is roughly 36 million kilometers. These distances may sound modest compared to the vastness of space, but in the context of a starship approaching a black hole, they define absolute boundaries. Cross the innermost stable circular orbit, and your ship must burn fuel continuously to avoid falling further. Stop your engines for even a moment, and the descent resumes. There is no neutral. There is no idle. The black hole does not allow you to rest. The innermost stable circular orbit matters for another reason that connects directly to the accretion environment. In astrophysics, this orbit defines the inner edge of the accretion disk, the swirling ring of matter that collects around a feeding black hole. Gas, dust, and shredded stellar material spiral inward, gradually losing energy through friction and radiation, settling into increasingly tight orbits until they reach this final stable ring. Inside that ring, the matter plunges directly toward the event horizon. The innermost stable circular orbit is, effectively, the edge of the cliff. Everything beyond it falls, and that accretion disk, that ring of spiraling matter, introduces the third zone of danger, one that does not depend on the ship crossing any orbital boundary at all. It depends only on proximity. Because the accretion environment around an actively feeding black hole is one of the most violent radiation sources in the known universe, when matter spirals toward a black hole, it does not fall quietly. It collides with other matter in the disk. Friction generates heat. The gravitational energy of the infilling material is converted into thermal energy with extraordinary efficiency, far more efficiently than nuclear fusion in a star. The inner regions of an accretion disk around a stellar mass black hole can reach temperatures of tens of millions of degrees. Around a supermassive black hole actively feeding at a high rate, the temperatures in the innermost regions can exceed 100 million degrees. At these temperatures, the disk radiates across the entire electromagnetic spectrum. Not just visible light, not just infrared, hard X-rays, gamma rays, a torrent of high-energy radiation that pours outward in every direction from the inner disk, creating a zone of lethality that extends far beyond the orbital boundaries we just described. A starship does not need to cross the photon sphere to be killed by the accretion disk. It does not need to reach the innermost stable circular orbit. It only needs to enter the radiation field surrounding the disk. And depending on the mass and feeding rate of the black hole, that field can extend for millions of kilometers. This is where the distinction between stellar mass and supermassive black holes becomes essential. It is also where most popular descriptions of black holes go completely wrong. The public imagination tends to treat all black holes as identical except for size. A bigger black hole is just a scaled up version of a small one. Same dangers, same physics, just more of it. That is incorrect in a way that matters enormously for anything trying to survive near one. A stellar mass black hole, with a mass of roughly 5 to 20 times our Sun, has a small Schwarzschild radius, on the order of 15 to 60 kilometers. Its event horizon is compact, but the tidal gradient, the difference in gravitational pull between 2 points separated by a short distance, is enormous near the horizon. The gravitational force on the bow of a starship would be measurably, destructively stronger than the force on its stern, even at distances well outside the event horizon. For a 10 solar mass black hole, the tidal stress reaches a level that would tear a human body apart at approximately 3,000 kilometers from the center. That is 100 times the Schwarzschild radius, 100 times the distance of the event horizon itself. The ship would be stretched along its length and crushed from the sides long before it ever reached the point of no return for light. Near a stellar mass black hole, the structure of the spacecraft fails first. The hull warps, the frame bends. The crew is pulled apart by a gradient so steep that no engineering material can resist it. This is spaghettification, and near a small black hole, it begins thousands of kilometers from the event horizon. A supermassive black hole presents an entirely different threat profile. With millions or billions of solar masses, its Schwarzschild radius is vast. The event horizon of Sagittarius A star sits approximately 12 million kilometers from the center. And because the tidal gradient depends on how quickly gravity changes over distance, and because the horizon of a supermassive black hole is so much larger, the tidal forces at the event horizon are gentle. Remarkably, almost paradoxically, a person falling toward a supermassive black hole could cross the event horizon without feeling any unusual tidal stress at all. Their body would remain intact. Their instruments would continue to function. They would not be spaghettified, at least not yet. But that gentleness at the horizon is deceptive. A supermassive black hole that is actively accreting matter is surrounded by one of the most energetic environments in the universe. Sagittarius A star is relatively quiet by supermassive black hole standards. It is not feeding aggressively. Its accretion rate is low, but many supermassive black holes at the centers of other galaxies are ravenous. The supermassive black hole in the galaxy M87, imaged by the Event Horizon Telescope, drives relativistic jets of plasma that extend for thousands of light years. Quasars, the most luminous objects in the known universe, are powered by supermassive black holes, feeding at rates so extreme that they outshine every star in their host galaxy combined. The accretion disks around these objects reach temperatures of millions of degrees. They radiate enough energy to sterilize entire solar systems. A starship approaching one of these objects would be bathed in lethal radiation long before tidal forces became relevant. So the question of what kills you near a black hole depends entirely on which kind of black hole you are approaching and what it is doing. Near a stellar mass black hole, the tidal gradient will tear you apart from the outside in. Near a supermassive black hole, the accretion environment may cook you, irradiate you, or blind your instruments long before the tides become a factor. And near either type, the orbital mechanics conspire to trap you the moment you descend past certain boundaries. Boundaries that sit well outside the event horizon. This is what the crew of that starship does not yet fully understand. They planned their approach around a single boundary, the event horizon. They calculated their safe distance based on where escape becomes impossible for light. But the zones of danger are layered. The accretion environment is the outermost. The innermost stable circular orbit sits below it. The photon sphere lies deeper still, and the event horizon is merely the final confirmation of what was already decided hundreds or thousands of kilometers earlier. The ship has entered the outer edges of the accretion zone. The radiation monitors have been climbing for the last hour. The crew expected elevated readings. That was in the mission plan, but the numbers are rising faster than the models predicted. The thermal load on the hull is increasing. The navigation system has begun to report inconsistencies. Distant stars that should appear in fixed positions are shifting, their light bent by the gravity they are descending into. The onboard clocks, synchronized before departure, are beginning to disagree with each other. Not dramatically. Not yet. But enough that the guidance computer flags an anomaly. And outside the ship, invisible and silent, the black hole waits. Not like a predator. Not like a trap. Like a landscape that changes the rules of motion for anything that wanders onto it. A slope so smooth you do not realize you are sliding until you try to stop. And by then, the next layer of danger is already reaching for the hull. The ship has not crossed the event horizon. It is not even close. But the black hole is already taking things from it. Accuracy, certainty, margin. And every kilometer deeper will cost more to recover than the last. What comes next is the radiation wall, and it does not ask permission before it begins to kill. The crew expected radiation. That was in the mission brief. Any approach to a feeding black hole would involve elevated exposure, and the ship's shielding was engineered for exactly this kind of scenario. Layers of high-density composite over a lead bismuth inner shell, backed by magnetic deflection systems designed to steer charged particles away from the inhabited sections of the hull. The shielding was tested against the hardest radiation sources known to spacecraft engineering. Solar particle events, galactic cosmic rays, the intense flux near magnetars. Every test was passed, every margin was met, and none of it was built for what is happening now. The radiation monitors began climbing 90 minutes ago. At first, the rise was gradual, a steady escalation consistent with the models. Then the curve steepened. The X-ray flux tripled in under 20 minutes. The gamma-ray detectors, which had been reading background noise since departure, crossed their first warning threshold and kept going. The thermal sensors on the sunward face of the hull, the side facing the accretion disk, are registering a heat load that the cooling system was never designed to sustain indefinitely. And somewhere in the medical bay, a dosimeter is ticking faster than any of the crew would like to think about. The ship has not entered the accretion disk. It is not plowing through the densest material. It is merely close enough to feel the environment that the disk creates. And that environment is among the most violent energy sources in the observable universe. To understand why, you need to understand what an accretion disk actually does. It is not a passive structure. It is not a ring of debris quietly orbiting a drain. It is a machine, a gravitational engine that converts the energy of falling matter into radiation with an efficiency that dwarfs anything else in nature. Here is how it works. When gas, dust, or shredded stellar material falls toward a black hole, it does not drop straight in. Angular momentum prevents that. The material spirals inward, forming a flattened rotating disk. As it spirals, particles on adjacent orbits move at slightly different speeds. The inner material orbits faster. The outer material orbits slower. This velocity difference creates friction between layers. That friction generates heat. And as the material moves to tighter and tighter orbits, falling deeper into the gravitational well, the energy released by each incremental step of descent grows larger. This is not a gentle process. Consider what is happening in physical terms. Matter is falling into one of the steepest gravity wells in the universe. Every meter closer to the center releases gravitational potential energy. The deeper the matter falls, the more energy comes out. And unlike a ball rolling down a hill, where the energy dissipates gradually into sound and heat, the matter in an accretion disk converts its gravitational energy into thermal radiation with extraordinary efficiency. The numbers are striking. Nuclear fusion, the process that powers every star in the sky, including ours, converts roughly 0.7% of the rest mass of hydrogen into energy. That is the reaction that lights the sun, that drives supernovae, that built every heavy element in your body. 0.7%. Accretion onto a non-rotating black hole converts approximately 6% of the rest mass of infalling matter into energy. That is nearly 9 times more efficient than fusion. And for a rapidly spinning black hole, where the innermost stable circular orbit is pulled closer to the event horizon by the rotation of space-time itself, the efficiency can reach 42%. 42% of the mass of everything that falls in is radiated away as energy before it crosses the event horizon. Nothing else in the known universe converts mass to energy that efficiently short of matter-antimatter annihilation. This is why accretion disks are so luminous. This is why quasars, supermassive black holes feeding at high rates in distant galaxies, can outshine every star in their host galaxy combined. Not by a small margin, by factors of hundreds or thousands. A single feeding supermassive black hole producing more light than 400 billion stars. The energy source is not nuclear. It is gravitational. And gravity, near a black hole, is the most powerful engine that exists. There is a natural speed limit on how fast this engine can run. Physicists call it the Eddington limit, named after the British astrophysicist Arthur Eddington, who first described it in the 1920s. The principle is straightforward. As matter falls inward and heats up, the radiation it produces pushes outward. That outward radiation pressure acts on the incoming material, slowing it down. At some accretion rate, the radiation becomes so intense that it pushes back as hard as gravity pulls in. The two forces balance. In theory, the black hole cannot eat any faster than this, because its own meal is generating enough light to blow the food supply away. In theory. In practice, some black holes violate this limit spectacularly. Observations have confirmed supermassive black holes in the early universe, feeding at rates that exceed the Eddington limit by factors of 10, 20, even 40 times what the physics should allow. The mechanism is not fully understood. The leading explanation involves the geometry of the accretion flow itself. If the infalling matter is dense enough and the flow geometry is right, particularly if the material funnels in along the plane of the disk, while radiation escapes preferentially through the polar regions, then the photons that should be blowing the food away are redirected out of the path of the incoming material. The brake fails. The engine runs unchecked. For a starship, this matters for a specific and terrible reason. The radiation environment around a black hole is not simply a function of the black hole's mass. It is a function of how aggressively the black hole is feeding, and whether it is feeding beyond its theoretical limit. A mission plan built around the expected radiation output of a black hole accreting at or below the Eddington limit could be catastrophically wrong if the actual accretion rate is several times higher. The radiation field would be proportionally more intense, the lethal radius would extend proportionally farther out, and the crew would discover the discrepancy only after entering the environment, when their instruments report flux levels that the models said were physically impossible. The universe does not respect theoretical maximums the way engineering textbooks do. Some black holes eat faster than they should, shine harder than the equations predict, and create radiation environments that exceed every conservative estimate. A starship that planned for the expected case would be unprepared for the actual one, And in this environment, unprepared and unshielded amount to the same thing. The temperature profile of the disk follows the energy release. The outer regions, where material orbits slowly and friction is modest, are relatively cool, thousands to tens of thousands of degrees. Moving inward, the temperature climbs. The middle regions reach hundreds of thousands of degrees, and the innermost zone, just outside the innermost stable circular orbit where the last stable orbits exist before the plunge, the temperature reaches its peak. For a stellar mass black hole of 10 solar masses, the inner accretion disk reaches approximately 10 million degrees. That is hotter than the core of most stars. At that temperature, the disk radiates primarily in X-rays, high-energy photons that pass through most conventional materials, the way visible light passes through glass. For a supermassive black hole feeding aggressively, the inner disk temperature depends on the mass and accretion rate, but even conservative estimates place it in the millions of degrees. The accretion environment around the supermassive black hole in the galaxy M87, captured in the first ever black hole image by the Event Horizon Telescope, drives plasma to estimated temperatures of billions of degrees in the flow surrounding its innermost regions. That is hundreds of thousands of times hotter than the surface of our sun. But the disk itself is only part of the radiation picture. Hovering above and below the disk, like a lethal atmosphere, sits a structure called the corona. The corona is a diffuse cloud of superheated plasma, electrons and ions that have been energized far beyond the temperatures of the disk surface. The mechanism that heats the corona is still an active area of research. Magnetic reconnection events, sudden releases of energy stored in twisted magnetic field lines, are the leading candidate. Whatever the cause, the result is plasma reaching temperatures of hundreds of millions to billions of degrees. Recent simulations of accretion onto stellar mass black holes show coronal electron temperatures exceeding 500 million degrees, with ion temperatures reaching tens of billions of degrees in the hottest regions. At these temperatures, the corona produces some of the hardest radiation in the accretion environment. Photons from the disk surface pass through the corona and are boosted to higher energies through collisions with superheated electrons, a process physicists call inverse Compton scattering. A soft X-ray photon enters the corona from below and exits as a hard X-ray or even a gamma-ray photon, its energy multiplied by factors of tens or hundreds. The result is a radiation field that extends across the full electromagnetic spectrum, from radio waves at the outer edges of the disk, through infrared and visible light in the middle regions, to ultraviolet, X-rays and gamma rays pouring out of the inner disk and corona. Now, consider what this means for a physical spacecraft. The ship's radiation shielding was designed for the interstellar medium. Galactic cosmic rays, mostly high-energy protons, arrive at a relatively steady, low rate. Solar particle events produce bursts of charged particles that magnetic deflection systems can largely redirect. The ship's composite hull absorbs what gets through. The inner lead bismuth layer catches most of the remainder. Under normal deep space conditions, the crew's cumulative radiation dose stays within acceptable mission limits. The accretion environment is not normal deep space conditions. X-ray radiation at the energies produced by a black hole's inner accretion disk does not behave like charged particles. It cannot be deflected by magnetic fields. X-ray photons are electrically neutral. They travel in straight lines and they penetrate. The ship's magnetic deflection system, the first and outermost layer of radiation protection, is useless against them. The photons pass through as though it does not exist. The composite hull absorbs some of the lower energy X-rays, but the harder photons, those boosted by the corona to energies of tens or hundreds of thousands of electron volts, penetrate deeper. They pass through the composite. They pass through the structural frame. They reach the lead bismuth layer, and even that absorbs only a fraction of the highest energy flux. What gets through enters the inhabited volume of the ship. Inside a human body, X-ray photons interact with tissue in two ways that matter for survival. They ionize atoms, stripping electrons from molecules, breaking chemical bonds in DNA, disrupting the cellular machinery that keeps tissue alive and functional. And they deposit energy, heating the tissue locally, creating microscopic damage tracks that accumulate with continued exposure. A single high-energy X-ray photon passing through a cell can break both strands of a DNA molecule simultaneously, creating a type of damage that the body's repair mechanisms struggle to fix. At low doses, the body copes. At the flux levels produced by an active accretion disk at close range, the damage rate overwhelms repair. The crew does not experience a slow accumulation of risk. They experience acute radiation syndrome, cellular death on a scale that becomes lethal within hours or days depending on the dose rate. Electronics fare no better. The ship's computers, navigation sensors, and communication systems rely on semiconductor circuits etched at microscopic scales. X-ray and gamma-ray photons passing through these circuits deposit charge in unintended locations, flipping bits, corrupting memory, triggering false signals. A single energetic particle strike can cause a soft error, a temporary glitch that the system can recover from. But at the flux levels near an accretion disk, soft errors do not arrive one at a time. They arrive in a continuous stream. The error rate exceeds the correction rate. Navigation data becomes unreliable. Sensor readings drift. The computers that the crew depends on to calculate their trajectory home begin to disagree with each other in ways that cannot be resolved by simply rebooting. The failure does not arrive all at once. It cascades. And the cascade follows a pattern that makes it particularly dangerous because each stage disguises itself as something manageable until the next stage reveals that it was not. It begins with isolated anomalies, a navigation fix that places the ship 300 meters from where the inertial measurement unit says it should be. A sensor reading that spikes briefly and then returns to normal. A log entry with a corrupted timestamp. Individually, these events are routine. Spacecraft experience single event upsets, transient errors caused by energetic particles, throughout any deep space mission. The systems are designed to catch them, flag them, and correct them. The crew notes the anomalies and moves on. The second stage begins when the correction systems themselves start absorbing hits. The error-checking algorithms that validate navigation data rely on redundant processing paths. 3 independent cores running the same calculation with a voting system that accepts the majority answer. This architecture tolerates 1 corrupted core out of 3. It does not tolerate 2. When the radiation flux is high enough that multiple cores experience upsets within the same processing cycle, the voting system breaks down. It produces an answer, but the answer is not reliable because the majority it selected was itself compromised. The crew sees a navigation fix that looks plausible. It is not flagged as an error, and it is wrong. The third stage is the most insidious. The crew begins to notice that two systems that should agree no longer do. The star tracker reports one orientation. The inertial measurement unit reports another. The difference is small, fractions of a degree, but it persists across multiple readings. The crew runs a diagnostic. The diagnostic software, running on the same radiation-degraded hardware, reports that both systems are functioning within normal parameters. The crew is now in a situation where they have two contradictory answers, no way to determine which one is correct, and a diagnostic tool that is itself untrustworthy. At this point, navigation becomes an exercise in judgment rather than measurement. The crew must decide which readings to trust based on experience, intuition, and cross-referencing against whatever independent data sources remain available. In interstellar space, that process is difficult. Near a black hole, where the very geometry of space distorts every external reference, it approaches impossible. The stars are in the wrong places. The disk is everywhere. And the instruments that are supposed to cut through the confusion are producing confident, precise, and potentially fictitious numbers. The crew does not lose navigation in a single dramatic failure. They lose it gradually, one reliable digit at a time, until the difference between knowing where they are and guessing where they are becomes indistinguishable from the inside. That is the point at which trajectory planning stops being engineering and starts being hope. Then there is the thermal load. The radiant heat from the accretion disk is not just energetic photons. It is raw thermal energy, infrared radiation pouring outward from a source that is millions of degrees hot. The ship's thermal management system is designed to reject heat into the vacuum of space using radiator panels. But radiators work by emitting infrared radiation, and they can only reject heat if the surrounding environment is cooler than the radiator surface. Near an accretion disk, the environmental thermal radiation can exceed what the radiators can shed. The ship absorbs heat faster than it can dump it. Internal temperatures rise, coolant loops reach their limits. Structural components designed to operate within a specific temperature range begin to soften, warp, or degrade. The hull does not need to melt for the ship to die from heat. It only needs to lose thermal equilibrium. Once the cooling system falls behind, the interior temperature climbs steadily, and every system aboard has a failure threshold that is now being approached. And the crew is dealing with all of this while trying to navigate. Gravitational lensing near a black hole does not merely distort the view, it dismantles it. Light from every direction in the surrounding sky is bent as it passes through the curved space-time near the black hole. Stars that should appear directly ahead are shifted to new apparent positions. Stars that should be behind the ship can appear beside it or even in front of it. Their light bent around the black hole and redirected toward the observer. The effect is not subtle. At distances of a few hundred Schwarzschild radii, the distortion is already visible. Constellations warp. Familiar patterns stretch and compress. Multiple images of the same star can appear in different parts of the sky simultaneously. Ghost copies created by a light, taking different curved paths around the gravitational well. Imagine walking down a corridor lined with funhouse mirrors on every wall, floor, and ceiling, where every mirror curves differently and the curvature changes with every step you take. That is what the sky looks like from inside a strong gravitational lensing field. The ship's star tracking navigation system, which determines orientation by matching observed star positions against a stored catalogue, cannot reconcile what it sees with what it expects. The stars are in the wrong places. Some appear doubled. Some have vanished entirely, their light bent so far that it no longer reaches the ship's sensors from any recognizable direction. The navigation computer flags error after error. It cannot determine which way the ship is facing with confidence because the very concept of direction has become dependent on the curvature of space-time. And that curvature is changing as the ship moves deeper. There is a specific relativistic effect that makes this even worse. Near a black hole, light arriving from the direction of the black hole is gravitationally blue shifted, compressed to shorter wavelengths and higher energies. Light arriving from behind the ship, from the direction of open space, is red shifted, stretched to longer wavelengths and lower energies. The result is an asymmetry in the radiation field. The forward-facing side of the ship receives harder, more energetic radiation than the rear. Sensors pointed toward the black hole are blinded by the intense blue-shifted flux. Sensors pointed away see a dim, reddened sky, where familiar stars have shifted into the infrared and become invisible to instruments calibrated for optical wavelengths. The crew is not just losing their ability to see where they are losing their ability to see at all. The accretion disk's own light, already powerful, is further amplified by gravitational lensing as it wraps around the black hole. Multiple images of the disk appear stacked on top of each other. The direct image, plus one or more secondary images created by the photons that orbited the black hole one or more times before reaching the ship. The visual field becomes a layered, smeared, overlapping confusion of warped light. Extracting useful spatial information from this image is not a problem the navigation system was programmed to solve. And there is one more element of the radiation environment that the crew was warned about in theory, but has no experience surviving in practice. Some accreting black holes produce relativistic jets. Twin beams of plasma launch perpendicular to the accretion disk at speeds approaching the speed of light. Not every black hole produces jets. The mechanism requires specific conditions, likely involving strong magnetic fields anchored in the inner accretion disk and the rotational energy of the black hole itself. But when jets are present, they represent the single most concentrated energy output in the accretion system. A relativistic jet is not a beam of light. It is a river of matter, electrons, positrons, possibly protons, accelerated to velocities exceeding 99% of the speed of light, and collimated into a narrow column that can extend for thousands of light years. The kinetic energy carried by the jet dwarfs the radiative output of the disk itself in some systems. The jet from the supermassive black hole in M87 extends roughly 5,000 light-years from the galactic center. A spear of plasma so energetic that it is visible across the electromagnetic spectrum from radio to gamma rays. A starship that passed through a relativistic jet, even at its outer edge, where the beam has dispersed and weakened, would be struck by a flux of relativistic particles so intense that no conceivable shielding could absorb it. The particles carry energies millions of times greater than those in a typical cosmic ray. Each one passes through the ship like a bullet through fog, depositing energy along its track, ionizing everything it touches, creating cascades of secondary radiation as it shatters atomic nuclei in the whole material. The heating effect alone would be catastrophic. The radiation dose would be lethal many times over within fractions of a second. Crossing a relativistic jet is not a survival scenario, it is annihilation. The ship would not burn, it would not melt, it would be irradiated so thoroughly and so quickly that the distinction between the ship and the energy passing through it would briefly cease to be meaningful. The ship in our scenario is not crossing a jet. Its approach vector was chosen to avoid the polar regions where jets typically form, but the crew now understands something that the mission planners underestimated. The accretion environment is not a single hazard at a single distance. It is a graduated assault that begins at enormous range and intensifies as distance decreases. The radiation does not wait for the ship to reach a specific boundary. It reaches outward, falls off with distance, but never drops to zero until the ship is far enough away that the black hole is just another point of light in the sky. The difference between a quiet black hole and an active one is the difference between walking through an empty furnace and walking through one at full heat. Both are the same structure. Both have the same geometry. But one will let you pass while the other will kill you before you are halfway through the door. Sagittarius A star, the supermassive black hole at the center of our galaxy, is currently in a relatively quiet state. Its accretion rate is low. It is not producing visible jets. The radiation environment around it, while elevated compared to interstellar space, is mild compared to what an active quasar produces. A starship approaching Sagittarius A star would face a fundamentally different radiation challenge than one approaching an actively feeding supermassive black hole in a distant galaxy. But quiet is relative. Even Sagittarius A star shows sporadic X-ray flares, sudden bursts of high-energy radiation that the Event Horizon telescopes supporting observatories detected during their imaging campaign. These flares are produced by magnetic disturbances in the residual accretion flow near the innermost stable circular orbit. They are brief, they are unpredictable, and they represent a reminder that a black hole does not need to be actively devouring a star to produce lethal radiation. It only needs a small amount of residual matter and a strong enough magnetic field. We know this because it has been directly observed. During the Event Horizon Telescope's imaging campaign of Sagittarius A star, a coordinated fleet of observatories monitored the black hole simultaneously across the electromagnetic spectrum. NASA's Chandra X-ray Observatory, the NuSTAR Space Telescope, and the Neil Gehrels Swift Observatory all watched the galactic center alongside the radio array. What they captured confirmed that even a quiet supermassive black hole is not truly still. Chandra and Swift recorded a faint X-ray flare during the observation window. A brief surge of high-energy radiation from the residual accretion flow. A second, moderately bright flare was detected by both Chandra and NuSTAR during the same campaign. These are not rare events. Sagittarius A star produces detectable X-ray flares roughly once per day on average, with some studies recording multiple flares within a single observing session. Each flare represents a sudden release of energy from the inner accretion region, likely triggered by magnetic field disturbances near the innermost stable circular orbit, where small quantities of residual gas are heated and accelerated by reconnection events. The flares vary in intensity. Some are faint, detectable by space-based X-ray telescopes, but modest by astrophysical standards. Others are substantially brighter, representing genuine surges in the radiation output from the inner environment. And crucially, their timing is unpredictable. No reliable periodicity has been established. The flares appear to occur stochastically, driven by the chaotic behavior of magnetic fields, threading through hot plasma in a regime of extreme gravitational curvature. There is no warning before a flare. There is no way to predict when the next one will come or how intense it will be. For a starship operating near Sagittarius A star, even in its quiet state, this means that the radiation environment is not constant. It fluctuates. The baseline may be survivable, but the baseline is punctuated by spikes that can multiply the local X-ray flux by significant factors within minutes. A ship whose shielding is calibrated to the quiet baseline, with perhaps a modest safety margin for expected variation, could find itself absorbing a flare dose that exceeds the margin entirely. The shielding holds against the average environment. It does not hold against the peaks, and the peaks arrive without notice, without pattern, and without mercy. A starship relying on the assumption that a quiet black hole means a safe approach would be gambling that no flare occurs during the closest phase of its trajectory. That is a wager against the behavior of magnetic fields in the most extreme gravitational environment in the universe. It is not a wager that any engineer would accept willingly. The crew of this ship is learning this in real time. The X-ray flux has leveled off, not because it is decreasing, but because the shielding has absorbed everything it can absorb, and the remaining radiation is now a steady presence inside the hull. The dosimeters confirm what the crew already suspects. They cannot stay at this depth indefinitely. The thermal load has pushed internal temperatures above the design range for several secondary systems. 2 sensor clusters on the forward hull have failed. Whether from radiation damage or thermal stress, the diagnostic cannot determine with confidence, because the diagnostic computer itself is experiencing intermittent errors. But the crew's most pressing problem is not the radiation behind them. It is the trajectory ahead. The ship has been decelerating into a lower orbit to capture close-range data. That deceleration was planned. What was not fully appreciated is what happens to the energy budget at this depth. The orbital velocity required to maintain a stable circular path at the ship's current distance from the black hole is a meaningful fraction of the speed of light. The ship is not traveling that fast. It is on a descending trajectory, not a stable orbit. And to arrest that descent, to convert the current plunge into a stable orbit, or, better, an escape trajectory, the engines will need to produce a velocity change that is significantly larger than anything the mission profile originally demanded. The radiation was supposed to be the obstacle. The crew now realizes it was only the introduction. Because the deeper problem is not energy pouring in. It is energy the ship does not have. Every kilometer closer to the black hole increases the velocity the ship needs to leave. Every second of descent adds to the deficit between what the engines can produce and what the escape trajectory demands. And at some point, a point that is not marked by a visible boundary, not announced by an alarm, not accompanied by any sudden change in the environment, the deficit becomes permanent. That point may already be behind them. What comes next is not about radiation. It is about the structure of the ship, the mathematics of escape, and the moment when the crew calculates the burn they need and discovers that the number is larger than everything their engines can give. The radiation did not destroy the ship. It degraded it. The hull is intact. The engines still function. The crew is alive. though their cumulative radiation dose is climbing toward levels that will require medical intervention if the exposure does not stop soon. 2 forward sensor clusters are offline. The navigation computer is operating on backup processing cores after soft errors corrupted the primary array. The thermal management system is running at capacity, barely holding interior temperatures within the survivable range. But the ship is still a ship. It still moves. It still has fuel. And the crew still believes they can recover the mission, pull up, arrest the descent, and begin the long burn back toward open space. They are wrong. Not because of the radiation they have already absorbed, though that damage is real. They are wrong because of 2 forces that are now acting on the hull in ways that no amount of shielding can deflect. One is gravity itself, pulling differently on different parts of the ship. The other is the mathematics of escape, which is about to close a door the crew does not yet know is shutting. The first of these forces is tidal. And to understand what it does, you need to understand something about gravity that most people never consider. Gravity is not a single pull. It is a field, a gradient that varies from point to point in space. Near Earth, this variation is negligible over short distances. The gravitational pull on your head is almost identical to the pull on your feet. The difference exists, but it is far too small to feel. It is the same force, applied almost uniformly across the height of a human body. Near a black hole, the word almost disappears. The gravitational field changes so rapidly with distance that 2 points separated by only a few meters can experience measurably different pulls. The side of the ship closer to the singularity is pulled harder than the side farther away. And this difference does not merely create a gentle imbalance. It creates a differential force that acts to stretch the ship along the radial direction, pulling the near side toward the black hole and the far side away from it, while simultaneously compressing the ship from the sides, squeezing it inward perpendicular to the direction of fall. Picture a machine that grabs an object at both ends and pulls in opposite directions while pressing inward from all sides. That is what tidal force does. The object is elongated and narrowed at the same time, stretched into a thinner and thinner shape, like soft candy being drawn through a taffy pull machine. In the language of astrophysics, this process has a name that is both vivid and precise: spaghettification. The object is pulled into a long, thin strand, a noodle of matter being drawn toward the singularity. The strength of the tidal force depends on 2 things: the mass of the black hole and the distance from its center. But the relationship between these 2 factors is not what most people expect. Increasing the mass of the black hole does not simply increase the tidal force at all distances. It changes where the tidal force becomes significant relative to the event horizon. And this is the key to understanding why stellar mass and supermassive black holes threaten a starship in fundamentally different ways. The tidal force at any given point near a black hole is proportional to the mass of the black hole, divided by the cube of the distance from its center. The cube is critical. It means the tidal force drops off extremely rapidly with distance. Move twice as far away, and the tidal force drops by a factor of 8. Move 10 times farther, and it drops by a factor of 1,000. This steep fall-off is why you do not feel tidal forces from ordinary objects in daily life. Even the moon's tidal effect on a human body is unmeasurably small. The tides you see in the ocean are cumulative effects over the entire diameter of the Earth, not forces that a single person could detect. But near a black hole, the distances are compressed. The event horizon sits close to the center of mass, absurdly close by astronomical standards. For a 10 solar mass black hole, the event horizon is roughly 30 kilometers out. At that distance, the cube law produces tidal accelerations that are staggering. Here is where the numbers become visceral. The human body can withstand a tidal stress of roughly 10 times the gravitational acceleration felt on Earth's surface before tissue begins to tear and bones begin to fracture. For a 10 solar mass black hole, that threshold is reached at approximately 3,000 kilometers from the center, 100 times farther out than the event horizon. A ship built from aerospace-grade titanium alloys has a higher structural tolerance than a human body, but not by as much as you might hope. The yield strength of the strongest materials available provides perhaps another order of magnitude of resistance. That extends the survivable distance inward, but not by enough to matter. The ship's structural frame would begin to deform at a distance still many times the Schwarzschild radius. Long before the crew could see the event horizon, if seeing it were even possible through the warped light and blinding radiation, the whole would be groaning under differential forces that its designers never anticipated. The deformation does not happen all at once. It builds. At a distance of 1,000 Schwarzschild radii, still enormously far from the event horizon by any intuitive measure, the tidal effect on a 100-meter spacecraft is effectively zero. Accelerometers at the bow and stern register identical readings. The ship's structural load is purely internal. Engine vibration, thermal expansion, the normal stresses of a pressurized hull. Nothing from the external gravitational environment contributes a detectable force. At 100 Schwarzschild radii, the first whisper arrives. It is not felt by the crew. It is not visible in any structural readout, but the ship's most sensitive gravimeters, instruments designed to measure variations in gravitational acceleration with extreme precision, begin registering a gradient. The pull at the bow of the ship is fractionally stronger than the pull at the stern. The difference is measured in billionths of a meter per second squared. It is scientifically interesting. It is structurally meaningless. The crew notes it in the data log and continues the descent. At 50 Schwarzschild radii, the gradient has increased by a factor of 8. Still small by engineering standards, but now large enough to produce a secondary effect. Fluid in the ship's coolant loops, which circulates through a closed system under pressure, begins to distribute asymmetrically. The forward reservoirs show slightly higher fluid pressure than the aft reservoirs. The difference is within normal tolerance. The coolant system compensates automatically. But the crew, if they are paying attention to the fluid management display, can see it. A persistent, slowly growing imbalance that was not present an hour ago. At 20 Schwarzschild radii, the gradient has become a physical presence. Unsecured objects, a stylus left on a console, a loose tool in the equipment bay, drift forward very slowly, drawn toward the bow by the fractional difference in gravitational pull. The drift is gentle, slower than the minute hand on a clock, but it is continuous and it is one-directional. The crew can see objects migrating towards the forward bulkhead. The effect is too slow to feel in their own bodies, but it is unmistakable when watched over minutes. The ship's interior has developed a subtle gravitational current, a tide within the hull that pulls everything slowly toward the side nearest the black hole. At 10 Schwarzschild radii, the gradient announces itself structurally. The ship's frame is now under measurable differential load. Strain gauges embedded in the primary structural members register tension along the longitudinal axis. The ship is being pulled slightly longer. And compression along the lateral axes. The ship is being squeezed slightly narrower. The values are small, well within the design margin, but they are persistent and they are growing. The hull is not flexing visibly, but the instruments confirm what the physics predicts. The ship is being gently reshaped by the gravitational field. At 5 Schwarzschild radii, the crew feels it. Not as a force. The tidal acceleration across the length of a human body is still below the threshold of perception at this distance from a 10 solar mass black hole, but as sound. The structural members of the ship, now under continuous and increasing differential load, begin to transmit vibrations through the hull. Low-frequency groans, felt more than heard, propagate through the deck plates. Rivets and weld joints that were engineered for the dynamic loads of engine operation. Forces that oscillate and reverse are now subjected to a static, unidirectional pull that does not release. The materials do not fail, but they speak. And what they are saying is that the ship was not built for this. Then those vibrations sharpen into something worse. Metal under tidal stress does not yield quietly. Sharp pings join the groans as microfractures begin propagating through the structure. Seams that held under launch forces and docking impacts begin to separate. The ship's internal pressure works against it now. The atmosphere inside pushes outward against a hull that is being pulled apart from outside. Small breaches form. The pressure differential accelerates the failure. What was a sealed hull becomes a compromised one. And in the vacuum of space near a black hole, a compromised hull is a death sentence for everyone inside. Near a stellar mass black hole, this process reaches its terminal phase at a distance where the event horizon is still far below. The ship does not fall into the black hole in any dramatic sense. It is disassembled, pulled apart into fragments. Those fragments are themselves pulled into smaller fragments. The smaller fragments stretch into filaments. The filaments elongate into threads of superheated matter, each thread tracing a slightly different orbital path due to the extreme curvature of space-time. The matter that was once a starship spirals inward as a ribbon of debris, radiating energy as tidal heating converts the ship's structural integrity into thermal emission. By the time the material reaches the event horizon, it bears no resemblance to the vehicle it once was. It is a stream of ionized atoms following a geodesic into the singularity. Spaghettification, in its complete form, is not just a stretching, it is a total mechanical deconstruction from engineered structure to elemental plasma, performed by gravity alone. Now contrast this with a supermassive black hole. The mass is millions or billions of times greater, but the event horizon is correspondingly larger. The Schwarzschild radius of Sagittarius A star is roughly 12 million kilometers. At that scale, the tidal gradient at the event horizon is gentle by the standards of what a spacecraft can endure. The difference in gravitational pull between the bow and the stern of a 100-meter ship crossing the event horizon of Sagittarius A star would be negligible. The hull would not flex. The crew would not feel any unusual force. They could cross the event horizon structurally intact, instruments still functioning, engines still operational. This seems like the better scenario. It is not. It is the worst one. Because crossing the event horizon of a supermassive black hole intact means the crew is alive and aware inside a region from which no escape is possible. The tidal forces that were gentle at the horizon do not remain gentle. They grow as the ship continues to fall inward toward the singularity. Somewhere below the horizon, the gradient reaches the same lethal thresholds that a stellar mass black hole imposes outside. The spaghettification happens regardless. It simply happens later, inside the event horizon, where no signal, no distress call, no record of what happened can ever reach the outside universe. The crew experiences every stage of the same mechanical destruction. They experience it while knowing they have already crossed the point from which no return is possible. That is not survival, it is prolonged awareness of an outcome that cannot be changed. But the ship, in our scenario, has not reached the event horizon of either type of black hole. It is still outside. The tidal forces are growing but have not yet exceeded the hole's structural limits. The crew still has time. What they do not have is an unlimited supply of something far more precious than structural integrity. They are running out of the ability to leave. Escape from a gravitational well requires energy. This is true near Earth, where a rocket must reach approximately 11 kilometers per second to break free. It is true near the Sun, where escape velocity at the surface is roughly 618 kilometers per second. And it is true near a black hole, where escape velocity follows the same fundamental principle, but reaches values that make every other gravitational well in the universe look trivial. The escape velocity from any point in space near a black hole depends on the distance from the center. The closer you are, the faster you need to travel to break free. At the event horizon, the escape velocity equals the speed of light. Since no material object can reach the speed of light, this is what makes the event horizon the point of no return. But the climb toward that limit does not happen in a sudden jump at the boundary. It happens gradually, continuously, along the entire approach path. At 10 Schwarzschild radii, the escape velocity is already a substantial fraction of the speed of light. At 5 Schwarzschild radii, it is higher. At 3, the innermost stable circular orbit for a non-rotating black hole, it has reached a value that demands relativistic engine performance just to maintain a stable orbit, let alone climb out. For a spacecraft, escape velocity translates directly into fuel. The ship's engines produce thrust by expelling propellant. The faster the ship needs to go, the more propellant it must burn. And the relationship is not linear. It is exponential. This is the tyranny of the rocket equation, and it applies with crushing force near a black hole. The rocket equation, published by Konstantin Tsiolkovsky in 1903, describes the relationship between the velocity change a spacecraft can achieve, its delta V, and the ratio of its fully fueled mass to its empty mass. The equation is logarithmic. To double your delta V, you do not double your fuel. You square your fuel ratio. To triple it, you cube the ratio. The practical consequence is that every additional increment of velocity becomes exponentially more expensive in propellant. At some point, no feasible amount of fuel can produce the required delta V because the fuel itself adds mass, which demands more fuel, which adds more mass, in a spiral that converges on impossibility. Near a black hole, this spiral tightens with every kilometer of descent. The escape velocity is rising. The delta V required to match it is rising faster. And the ship's fuel reserves are finite, fixed at whatever amount was loaded before departure. There is no refueling station. There is no resupply. The fuel the ship carries right now is all the fuel it will ever have. And every second of descent burns that reserve further because of maintaining even a decaying orbit at these depths requires constant thrust to counteract the curvature of space-time that pulls every free-falling object inward. The innermost stable circular orbit, which we defined earlier as the boundary below which no stable orbit exists, takes on its full lethal meaning here. Above this boundary, a ship can, in principle, maintain a circular orbit without firing its engines. The orbit is stable. A small perturbation, a brief thruster misfire, a slight change in velocity will not send the ship spiraling inward. It will oscillate around the stable orbit and return to it, the way a marble oscillates in the bottom of a bowl. The ship can coast. It can conserve fuel. It can wait. Below the innermost stable circular orbit, that stability vanishes. The bowl inverts. A marble placed on the rim of an inverted bowl does not oscillate. It slides off. Any perturbation, no matter how small, sends the object on a trajectory that curves inward toward the event horizon. The only way to resist this descent is continuous powered thrust, engines firing constantly, burning fuel every second, fighting the geometry of space-time itself to hold position. And the fuel cost of that fight increases as the ship descends, because the curvature it is fighting grows steeper with every meter. The crew of the ship is now below the innermost stable circular orbit. They did not cross it deliberately. The descent that brought them through the radiation zone carried them past this boundary while they were focused on managing thermal loads and radiation damage. The transition was not marked by any physical sensation. There was no bump, no flash, no alarm specifically tied to the orbital stability limit. The ship simply passed from a region where its orbit could sustain itself into a region where it cannot. And the difference between those two regions is the difference between a ship that can choose to leave and a ship that must fight to leave, and must fight harder with every passing second. The navigation computer, despite its radiation-damaged processing cores, can still calculate trajectories. The crew asks it the only question that matters now: what burn is required to escape? The answer comes back in delta V. The number is large. It is larger than the crew expected. It accounts for the current depth, the current velocity, the current trajectory angle, and the gravitational field at this radius. The ship's engines are powerful. Its fuel reserves, while partially consumed by the approach and station-keeping burns, are still substantial. The crew compares the required delta V against the remaining propellant, and there it is, the number they cannot close. The required delta V exceeds the ship's maximum capacity, not narrowly, not by a margin that could be closed with clever trajectory design or a more efficient burn profile. The deficit is structural, a gap between what the engines can produce and what the gravity well demands that no optimization can bridge. The crew does not accept this immediately. No crew would. The first response is to check the calculation. The navigation officer clears the input buffer, re-enters the ship's current position, velocity, mass, and remaining propellant from the raw sensor data, and runs the escape trajectory computation again from scratch. The second result matches the first. The delta V required is the same. The fuel capacity is the same. The deficit is the same. The second response is to challenge the assumptions. Perhaps the position estimate is wrong. The radiation-degraded navigation system might be placing the ship deeper than it actually is. A shallower actual position would reduce the required delta V. The crew cross-references the primary navigation fix against the backup inertial measurement unit, against the Doppler shift of the relay beacon signal, against the apparent angular size of the accretion disk. The estimates disagree slightly, as damaged systems do, but they cluster within a narrow range. The ship is where the computer says it is. The depth is real. The third response is to reconfigure the burn. Perhaps a different thrust angle, not directly outward, but along a shallow spiral that trades time for efficiency, could reduce the total delta V by exploiting the orbital mechanics more carefully. The computer evaluates a family of escape trajectories across a range of initial thrust vectors. Some are marginally more efficient than the direct radial burn. None of them close the gap. The most efficient trajectory in the set reduces the deficit by less than 4%. The remaining 96% of the shortfall stands. The fourth response is to reduce the ship's mass. Every kilogram jettisoned improves the fuel-to-mass ratio and increases the achievable delta V. The crew inventories everything aboard that is not structurally essential. Scientific instruments, sample containers, secondary stores, furniture, non-critical hull plating. The total mass of everything that could theoretically be thrown overboard is calculated. The rocket equation converts that mass reduction into additional delta V. The number improves. It does not improve enough. Even stripping the ship to its structural skeleton and engines would not produce the delta V required, because the fuel itself constitutes the majority of the remaining mass, and the logarithmic nature of the rocket equation means that each additional kilogram jettisoned produces a smaller and smaller increment of performance. The crew sits with the numbers. They have checked them 4 ways. They have challenged every input. They have explored every alternative, and the conclusion has not changed. The arithmetic is not wrong. The ship is below its own escape threshold, and nothing aboard can alter that fact. The reason is cumulative. Every kilometer of the approach consumed fuel. The initial deceleration to enter a study orbit burned fuel. Station keeping against the orbital instabilities burned fuel. The attitude adjustments to manage the thermal load from the accretion disk burned fuel. Each of these expenditures was individually modest. Together they consumed enough of the reserve to move the break-even point, the depth from which the remaining fuel could still achieve escape, above the ship's current position. The ship descended past its own point of no return without anyone aboard recognizing the moment it happened. This is the cruelest feature of the geometry. The point of no return for the ship is not the event horizon. It is not the innermost stable circular orbit. It is not the photon sphere. It is a location defined entirely by the ship's own specifications, its remaining fuel, its engine efficiency, its current mass, its current depth. 2 different ships with different fuel loads would have different points of no return at different distances from the same black hole. The boundary is not a property of the black hole. It is a property of the ship. And because it depends on variables that change continuously, fuel decreasing, depth increasing, required delta V growing, the boundary moves. It moves inward as long as the ship descends. And at some moment, it moved past the ship's position. That moment is already gone. The crew runs the numbers again. They adjust parameters. They consider jettisoning non-essential mass to improve the fuel-to-mass ratio. The navigation computer evaluates slingshot trajectories that exploit the black hole's rotation. If the black hole is spinning, the ergosphere provides a region where rotational energy can, in theory, be extracted by an object on the right trajectory. The crew explores every option the physics allows. One option demands a longer examination, because it is the only one grounded in a real physical mechanism that could, in principle, add energy to the ship from the environment itself. It is called the Penrose process, and it depends on a property of spinning black holes that has no analogy anywhere else in physics. Most black holes rotate. The stellar cores that form them were spinning before they collapsed, and conservation of angular momentum means the resulting black hole retains that rotation. A spinning black hole is described not by the Schwarzschild solution, but by the Kerr solution, published by New Zealand mathematician Roy Kerr in 1963. And the Kerr solution predicts a region outside the event horizon that does not exist around a non-rotating black hole. It is called the ergosphere. The ergosphere is not a sphere in the usual sense. It is an oblate region, bulging at the equator and flattened at the poles, that surrounds the event horizon of a spinning black hole. Inside the ergosphere, space-time itself is rotating. Not matter, not radiation. The fabric of the universe is being dragged around by the spin of the black hole in a process called frame dragging. Within the ergosphere, this dragging is so extreme that nothing, no object, no particle, no beam of light, can remain stationary relative to the distant stars. Everything inside the ergosphere is forced to co-rotate with the black hole, regardless of how powerful its engines are or which direction they are pointed. You can fire your thrusters directly against the rotation. You will still rotate. Space-time itself is moving, and you are embedded in it. The Penrose process exploits this forced rotation. In theory, an object can enter the ergosphere, split into two pieces, and arrange the split so that one piece falls into the black hole on a retrograde trajectory, against the spin, while the other piece is flung outward with more energy than the original object carried in. The energy comes from the rotational energy of the black hole itself. The black hole slows down fractionally. The escaping piece gains kinetic energy. It is the most direct known mechanism by which a physical object can extract energy from a black hole. The crew calculates the trajectory. The mathematics are real. The energy gain is real. But the trajectory required to execute the process is not survivable. The ship would need to descend into the ergosphere, deeper than its current position, deeper into the tidal field, deeper into the radiation environment, then execute a precise split maneuver at a specific point in the orbit, jettisoning mass on an exact retrograde vector, while the remainder of the ship catches the energy boost on the outbound leg. The precision required is extreme. The margin for error is effectively zero. And the tidal forces within the ergosphere at this black hole's mass would be applying destructive loads to the hull throughout the maneuver. The ship would need to survive the descent, execute a structural separation under tidal stress, and then ride the energy boost outward through the same radiation field it barely survived on the way in, all with engines that are already operating at capacity and fuel reserves that are already insufficient. The Penrose process is real physics. It is not a real option. The energy it could provide is a fraction of the deficit. The cost of reaching the extraction point exceeds the gain, and the risk of losing the ship entirely during the maneuver approaches certainty. The crew files the calculation and moves on. The mathematics do not lie. The propellant is finite. The gravity well is not. And the difference between those two facts is now the only thing that determines the ship's future. There is a moment in every engineering failure when the system passes from damaged to doomed. It is not the moment of the explosion. It is not the moment the beam breaks. It is the earlier moment, the quieter one, when the load exceeded the capacity and the structure began to yield in a way that could not be reversed. The failure propagates from that point forward. Everything that happens afterward, the visible collapse, the noise, the destruction, is a consequence of the moment that already passed. The ship passed that moment. It passed it in silence. No alarm sounded. No hull plate buckled. The crew was managing radiation exposure and thermal loads, and did not notice the fuel gauge cross the threshold that separated a mission from a trajectory. The black hole didn't seize the ship. It did not pull it across a glowing boundary. It simply waited while the ship spent its own reserves, descending voluntarily deeper into a well from which the exit cost was rising faster than the remaining capacity could cover. The crew now faces a choice that is not really a choice. They can burn everything they have in a maximum escape attempt, knowing the trajectory will fall short. This buys time, perhaps hours, perhaps longer, depending on how high the partial escape arc carries them before it curves back down. During that time, the ship would climb to a shallower depth, where the radiation is less intense and the tidal forces are weaker. It would be a reprieve, not a rescue. The arc would peak and the ship would begin to descend again, this time with empty tanks and no possibility of a second attempt. Or they can conserve fuel and attempt to hold position, using controlled burns to slow the descent, extending the time they have at a survivable depth. This preserves the option of rescue, if a second ship exists, if it can reach this depth, if it can arrive in time. But holding position inside the innermost stable circular orbit requires continuous thrust. The fuel consumption is relentless, the reserves drain steadily, and the clock that measures how long the ship can sustain this hold is measured in hours, not days. Either way, the ship is descending. The only variable is how fast. There is one possibility the crew has not yet fully confronted. They cannot save themselves, but perhaps someone else can save them. A second ship, dispatched from the mission's support fleet, carrying fresh fuel, intact systems, and a crew that has not spent hours absorbing a radiation inside a gravity well. If that ship exists, and if it can reach their position, and if it can carry them out, then the mission is disaster, but not a death sentence. The crew calculates what a rescue would require. The numbers are not encouraging. A rescue ship approaching from outside the gravitational well would need to descend to the stranded crew's current depth. That descent carries the same cost the original ship already paid: fuel for deceleration, radiation exposure during transit through the accretion environment, thermal load on the hull, navigational degradation from lensing. The rescue ship faces every hazard the original ship encountered, with one additional burden. It must carry enough fuel not merely to descend and return, but to carry the additional mass of the stranded crew and any equipment transferred between ships. The rocket equation applies to the rescue ship just as mercilessly as it applies to the original, and the equation punishes additional payload mass exponentially. Doubling the payload does not double the fuel requirement. It compounds through the logarithmic relationship, demanding a fuel load that grows far faster than the mass being rescued. The crew computes the minimum specifications for a rescue ship capable of reaching their current depth and returning with their crew aboard. The required fuel capacity is enormous, many times larger than their own ship's original reserves. The required radiation shielding exceeds any standard deep space specification. The required engine performance demands sustained thrust levels at the upper boundary of what current propulsion technology can deliver. Such a ship may exist in principle. Whether it exists in practice and whether it could be launched, navigate to the correct approach vector, and execute the descent within the time window that the stranded crew's supplies and radiation tolerance allow. That is a question the crew cannot answer from where they are. But there is a deeper problem, one that does not depend on the rescue ship's specifications at all. The stranded ship is still descending. Every hour it sinks deeper, the rescue becomes harder. The required fuel for extraction increases. The radiation environment the rescue ship must enter intensifies. The tidal loads on both vessels during the docking and extraction maneuver grow. There is a depth, and it is calculable, below which no rescue ship of any conceivable design can reach the crew and return. Below that depth, rescue is not a matter of building a better ship or carrying more fuel. It is physically excluded by the relationship between the energy required and the energy available in a finite universe. That depth is not the event horizon, it is far above it, and the stranded ship is approaching it on a trajectory that the crew can slow, but cannot stop. The crew makes their calculations, they make their choice, and as the engines fire and the ship fights for every meter of altitude against a force that has never lost, a new problem arrives. One that the crew cannot solve with fuel or thrust or engineering skill. It arrives in the form of a clock discrepancy. The ship's master clock, synchronized to a reference frame in open space before departure, is now running measurably slower than the reference signal they can still faintly receive. Time aboard the ship is no longer passing at the same rate as time for the rest of the universe, and what that means for the crew, for any hope of rescue, and for the very possibility of communication with anything outside this gravity well, is the subject that will close this story. Because the black hole is not finished, it has taken the ship's fuel margin, it has damaged the ship's systems, it is pulling the ship's structure toward failure, and now it is taking the one thing the crew assumed was universal and constant, and beyond the reach of any force in nature. It is taking their time. The clocks disagree, not by much, not yet. The ship's master clock, running on a cesium oscillator calibrated to a reference frame in open space, is ticking at a rate that is measurably slower than the timing signal still arriving from the mission relay beacon parked far outside the gravitational well. The discrepancy is small, fractions of a second accumulated over the last several hours, but it is real, it is growing, and it is not caused by a malfunction. The clock aboard the ship is working perfectly. Every atom of cesium is oscillating at exactly the frequency it should. The problem is not with the clock. The problem is with time itself. This is gravitational time dilation, and it is one of the most experimentally confirmed predictions in all of physics. Time does not flow at the same rate everywhere. It flows slower in stronger gravitational fields. This is not a metaphor. It is not an illusion caused by signal delay. It is a physical fact about the structure of the universe. A clock at sea level on Earth ticks slightly slower than a clock on a mountaintop. The difference is tiny, billionths of a second per day, but it has been measured with atomic precision and confirmed beyond any reasonable doubt. The global positioning system satellites orbiting Earth must correct for this effect continuously. Without the correction, navigational accuracy would drift by roughly 10 kilometers per day. Gravitational time dilation is not a theoretical curiosity. It is an engineering constraint that affects infrastructure you use every morning. Near a black hole, the effect is not tiny. It is dramatic. The gravitational field near a black hole is so intense that time dilation becomes a dominant factor in everything that happens. At a distance of 10 Schwarzschild radii from a non-rotating black hole, a clock runs approximately 5% slower than a clock at infinity. At 5 Schwarzschild radii, the dilation increases substantially. At 3 Schwarzschild radii, the innermost stable circular orbit, a clock runs roughly 18% slower than a distant reference clock. And as the distance shrinks toward the event horizon, the dilation approaches its limit. At the event horizon itself, time, as measured by a distant observer, stops completely. A clock falling toward the horizon would appear, from outside, to tick slower and slower and slower, asymptotically approaching zero without ever quite reaching it. The falling object appears to freeze at the boundary, its image dimming as the photons it emits are stretched to longer and longer wavelengths by the gravitational redshift, fading from visible light into infrared, into microwave, into radio, and finally into wavelengths so long that no instrument could detect them. From the outside, the object never crosses the horizon. It just fades away. From the perspective of the object itself, from the perspective of the crew aboard the falling ship, the experience is completely different. They do not feel time slowing down. Their clocks tick normally by their own local measurement. Their conversations proceed at a normal pace. Their heartbeats, their thoughts, their perceptions all function without any subjective change. Time dilation is not something you experience from the inside. It is something the rest of the universe experiences about you. And that asymmetry is what makes it lethal in the context of rescue. Consider the crew's situation. They are deep inside the gravitational well. Their fuel is insufficient for escape. They are attempting to hold position using controlled burns, but their reserves are draining and their altitude is slowly decreasing. Their only hope is external rescue, a second ship, launched from safety, descending to their depth, matching their orbit, and pulling them out. But the time dilation means that the crew's experience of time and the rescue ship's experience of time are no longer synchronized. Every hour that passes aboard the stranded ship corresponds to more than an hour passing in the outside universe. As the stranded ship descends further, the ratio worsens. A day aboard the ship might correspond to days or weeks outside. And this is not a communication delay caused by signal travel time. This is a genuine difference in the rate at which time passes. The rescue ship is aging faster than the crew it is trying to save. At first glance, this might seem like an advantage for the crew. They experience less time. They age more slowly. But the advantage is an illusion. The rescue ship must still travel to the stranded crew's location. That journey takes time, measured in the rescue ship's own reference frame. And the deeper the stranded crew has fallen, the more extreme the gravitational environment the rescue ship must enter to reach them. The fuel mathematics of rescue were already impossible. The crew computed that before the clocks began to diverge. But time dilation adds a dimension that propellant calculations alone do not capture. A rescue ship planning a descent based on the stranded crew's last reported position will find them deeper than expected when it arrives, because the stranded ship continued to sink during the transit time, and that transit time was longer in the rescue ship's reference frame than the crew experienced aboard. The target is falling, while the rescuer ages faster. The fuel budget, calculated for the depth the crew reported, is no longer sufficient for the depth the crew has actually reached by the time the rescue ship gets there. Every hour of delay in the outside universe pushes the stranded ship further below the threshold that was already uncrossable, and the hours themselves are no longer the same length for the two vessels. The rescue ship is chasing a target that is falling into a region where time itself conspires to widen the gap between intention and arrival. The stranded crew may still be alive. They may still be conscious. They may still be transmitting distress signals, but the signals they send are being gravitationally redshifted. Their frequencies stretch to lower and lower values as the photons climb out of the gravity well. A radio transmission sent at a standard frequency arrives at the rescue ship's position, shifted toward longer wavelengths, weakened, distorted. The deeper the stranded crew falls, the more extreme the redshift. Eventually, the signal drops below the sensitivity threshold of any receiver. The crew is still broadcasting. The universe can no longer hear them. And from the crew's perspective, the opposite effect distorts incoming signals. Transmissions from the rescue ship, sent at normal frequencies, arrive at the stranded crew's position blue shifted, compressed to higher frequencies and higher energies. The rescue ship's voice, if it could be heard at all, would arrive as a high-pitched, accelerated stream, the words compressed into a fraction of their original duration. The two reference frames are drifting apart. Communication becomes distorted, then fragmented, then impossible. Not because the equipment fails, because the fabric of space-time between sender and receiver is stretched to the point where information cannot survive the journey intact. Two people standing on opposite rims of a canyon that widens faster than sound can cross will eventually lose the ability to hear each other. They can scream. They can cup their hands around their mouths. They can amplify their voices with every tool available. It does not matter. The canyon is growing. The sound waves stretch and weaken as they cross. And at some width, silence is not a choice. It is a fact of geometry. This is what is happening to the crew. The canyon between them and the rest of the universe is widening. Not in space. The distance to the event horizon may still be millions of kilometers. In time. The temporal distance between their reference frame and the reference frame of anyone who could save them is growing, stretching every signal, every plan, every possibility thinner and thinner until it snaps. Now let us ask the question that drives the rest of this story. At what point was the ship doomed? Not destroyed, not spaghettified, not incinerated by the accretion disk. Doomed. The point at which no sequence of actions available to the crew or anyone else in the universe could result in the ship and its crew returning to safety. When did that moment occur? It was not when the tidal forces began to flex the hull. The hull was still intact at that point. It was not when the radiation dosimeters crossed the warning threshold. The crew was still functional. It was not when the navigation computer began reporting errors. The ship could still maneuver. It was not when the fuel calculation showed a deficit. There are degrees of deficit. A ship short on fuel can still attempt a partial escape, reach a shallower orbit, and wait for a rescue that might be feasible from that higher altitude. The moment of doom was the point at which the combined total of the ship's remaining fuel capacity, structural integrity, radiation tolerance, thermal margin, navigational accuracy, and crew health collectively fell below the minimum required for any escape trajectory, including those that involved external rescue. It was not a single variable crossing a single threshold. It was the simultaneous exhaustion of every margin the ship had. Fuel was low. Structure was degrading. Radiation exposure was accumulating. Thermal load was approaching limits. Navigation was compromised. And time dilation was stretching the window for external assistance beyond any realistic response time. Each of these factors, considered individually, might have been survivable. A ship with damaged sensors but full fuel tanks could escape. A ship with low fuel but intact structure could hold position and wait for rescue. A ship with high radiation dose but functional navigation could make an emergency burn for the fastest available exit trajectory. It is the simultaneous failure of all margins that creates the condition from which no recovery is possible. And near a black hole, simultaneous failure is not bad luck. It is the design of the environment. Every kilometer closer to the center degrades every variable at the same time. Fuel cost rises, tidal stress increases, radiation intensifies, time dilation deepens, navigation accuracy deteriorates. The black hole does not attack one system. It taxes all of them together. And the total load exceeds the total capacity at a point that depends on the ship, but is always outside the event horizon. This is the deepest truth about black holes, and the one that most descriptions never reach. The event horizon is not the danger. The event horizon is the endpoint of a process that began much earlier and was already irreversible, long before the ship got anywhere near it. The real boundary is not a place. It is a condition. The condition in which the total resources of the ship, measured against the total demands of the environment, tip from positive to negative. That condition is reached at a different radius for every ship. A more powerful ship with better shielding and more fuel reaches it deeper. A weaker ship reaches it higher. But every ship reaches it. And every ship reaches it outside the event horizon. What we call too close is not a distance. It is a relationship. A relationship between what the ship has and what the black hole demands. And the black hole always demands more than any ship can carry, because the cost of proximity rises without limit, while the ship's resources are finite. Somewhere between the safe distance where the mission began and the event horizon where physics draws its final line, those two curves cross. The demand exceeds the supply. And from that crossing point forward, the ship is not approaching a black hole. It is completing a process that has already been decided. There is a way to think about this that strips away the astrophysics and reveals the structural horror underneath. Imagine a staircase. Each step takes you one level deeper into the gravity well. Each step costs something: fuel, shielding capacity, structural tolerance, time. The steps behind you dissolve after you stand on them. You cannot go back to a previous step. You can only go forward, down, or remain where you are, which itself costs fuel to maintain. And with each step forward, the next step grows taller. The cost increases. You're carrying fewer resources with every step, because each one took a piece of what you had. The stairs behind you are gone. The stairs ahead are larger. And at some point, you look up and realize you cannot reach the top anymore. Not because the staircase collapsed, because you spent what you had on the steps that brought you here, and what remains is not enough for the steps that remain. That is what proximity to a black hole does to a starship. It does not need to swallow the ship. It does not need to pull it across the event horizon. It only needs to let the ship keep descending while the costs compound and the resources deplete. The black hole is patient. It does not accelerate the process. It does not cheat. It simply allows the mathematics to work. And the mathematics are merciless. The crew of the ship understands this now. They have run every scenario. They have computed every possible burn sequence. They have considered every option: slingshot trajectories, mass jettison, differential thrust to fight the tidal gradient, low power survival mode, to extend the fuel for station keeping. Every calculation terminates at the same conclusion: the ship cannot return. What the crew does with this knowledge is not a question of physics. It is a question of something much older and much harder. The chief engineer returns to the navigation console and begins running trajectory sequences again. She knows the answer has not changed. The propellant has not increased. The gravity well has not weakened. But the act of entering parameters, of watching the computer trace arcs across a coordinate grid, of reading the output and comparing it against the last run, that act is the only thing she has done for 20 years that still feels like herself. She is not solving the problem. She's being the person who solves problems for as long as being that person is still possible. When the fuel runs out and the console goes dark, that identity will go with it. She is not ready to let it go before she has to. Across the compartment, a communications officer speaks into a recorder. He is composing a message to his daughter. He speaks slowly. He chooses each word with care. He knows that the transmission, if it is sent, will be redshifted beyond recognition long before it reaches any receiver. The words stretched into wavelengths that no antenna will ever register as language. The message will not arrive. He records it anyway. The act of speaking to someone who cannot hear him is irrational. It is also the most human thing happening aboard this ship. He finishes. He pauses. He starts a second message, this one to no one in particular. A description of what the instruments are reading. A summary of what went wrong and when. A record composed for an audience that may not exist, in a format that may not survive, transmitted into a medium that will erase it before it travels a single light year. He sends it anyway. The alternative is silence, and he's not ready for silence yet. Near the forward observation port, a third crew member has stopped working entirely. She's watching the accretion disk. From this depth, it fills a significant portion of the visible sky. A warped, layered river of light curving around the darkness ahead. Bands of superheated matter tracing arcs that no geometry built for flat space can explain. The secondary photon ring glows inside the primary image, a thin, bright echo nested within the larger glow. The shadow at the center is absolute. It is the darkest thing she has ever seen. Not dark like a shadow on a wall, not dark like a room with the lights off, but dark like the concept of light has been removed from that region of space and nothing has been left in its place. She has studied black holes for most of her career. She has seen simulations, renderings, the reconstructed images from the Event Horizon telescope. None of them prepared her for the scale of it, the silence of it, the way the light wraps around the void with a smoothness that makes violence look like grace. She does not speak. She does not record. She watches. It is the most extreme structure the universe builds, and she is seeing it from closer than any human was ever meant to be. That is not nothing. In the hours she has left, that is not nothing at all. The black hole does not know they are there. It has no awareness, no intention, no malice. It is a region of space-time whose geometry was set by the distribution of mass within it. Following equations published over a century ago by a physicist who solved them while serving on the front lines of a war. The black hole is not a predator. It is not a trap. It is a landscape. And the crew drove into it because they underestimated the cost of the terrain. Every safety protocol, every mission plan, every simulation that modeled this approach treated the event horizon as the boundary that mattered. Stay above it and you are safe. Cross it and you are lost. That framing was not wrong. It was incomplete. The event horizon is the boundary that matters for light. It is the boundary that matters for information. It is the boundary that defines the black hole as a physical object. But for a starship, a finite machine with finite fuel, finite shielding, finite structural strength, and a crew that ages and breathes and breaks, the boundary that matters is far above the event horizon. And it is not the same for every ship, and it is not marked, and it does not announce itself when you cross it. The universe does not owe you a warning. It does not draw a line and say this far and no further. Near a black hole, the line is invisible, personal, and final. It is defined by what you brought with you and what you spent along the way. And by the time you know where it was, you are already below it. This is the answer to the question that opened this story. What happens if a starship gets too close to a black hole? The answer is not spaghettification. That is one possible outcome, the physical endgame near a stellar mass black hole. But it is the last chapter, not the story. The answer is not radiation death, though that is another possible endgame near an active accretion disk. The answer is not even crossing the event horizon, because many ships will be doomed long before they reach it. The answer is this: the ship enters an environment where every resource it has is being consumed simultaneously, and where the cost of leaving increases faster than any resource can be replenished. At some point in that descent, the total cost of escape exceeds the total capacity of the ship. From that moment forward, the ship is not in danger of falling into a black hole. It is completing a trajectory whose outcome was determined by a crossing point that is already in the past. The crew may still be alive. The engines may still be firing. The hull may still be intact. But the relationship between what the ship has and what the universe demands has already been settled. And the settlement is final. A black hole does not need to consume a starship to end its mission. It does not need to drag it past the event horizon. It does not need to spaghettify it or incinerate it or crush it. It only needs to exist. Its gravity, its radiation, its tidal forces, and its warping of time create an environment where proximity has a compounded cost and retreat has a rising price. Those two curves cross, they always cross. And where they cross is where the mission ends, not at the event horizon, not at the singularity, at the quiet, unmarked, invisible point where the ship spent the last of what it needed to leave. The black hole did not take the ship. The ship gave itself away, 1 kilometer at a time, one burn at a time, one decision at a time, descending into a well where every step cost more than the last, and none of them could be taken back. And the most disturbing part of this entire story is not the violence of what happens near a black hole. It is the silence of it. The tidal forces build slowly, the radiation accumulates steadily, the fuel depletes smoothly, the time dilation deepens gradually. There is no single catastrophic moment. There is no explosion, no alarm, no dramatic event that separates before from after. There is only a continuous, quiet, irreversible slide from a ship that could leave into a ship that cannot. The transition happens in the same way that dawn becomes morning, not at a boundary, but along a gradient so smooth that you cannot point to the instant it changed. That is what makes a black hole the most dangerous object in the universe for anything that moves under its own power. Not because it is violent, though it can be. Not because it is sudden, though tidal destruction near a small black hole is swift. But because it is patient, and because the point of no return is never where you think it is. It is always higher. It is always earlier. And it is always behind you by the time you think to look for it. The ship in this story was doomed the moment it committed to a trajectory that spent more margin than the return could afford. That moment was not dramatic. It was a navigation decision, a fuel allocation, a thermal management compromise. It was the ordinary business of operating a spacecraft in an extraordinary environment. And it was irreversible. The stars outside the ship are still shining. The universe beyond the gravity well is still there. The crew can still see it, dimmed and reddened and warped by the curvature of the space-time they are trapped in, but present. The light from those stars left its source years or centuries ago, and travelled in straight lines across the emptiness to reach this place, only to be bent and stretched by the geometry of a mass the stars will never touch. The crew sees the universe through a lens that is slowly closing. Somewhere out there, beyond the accretion disk, beyond the lensing field, beyond the tidal zone, beyond every boundary described in this story, there is a distance at which the black hole is just another point of mass in the sky, a place where the escape velocity is modest, the tidal gradient is undetectable, the radiation is background noise, and time passes at the same rate as everywhere else. A place where a ship with the same fuel, the same shielding, the same crew, the same engines, could turn around with a single burn and fly home without difficulty. That place exists. It always existed. And the distance between it and where the ship is now is not measured in kilometers. It is measured in the decisions that were made along the way. Each one reasonable, each one small, each one taking the ship a little deeper into an environment that returns nothing it takes. Near a black hole, too close is not a line you cross. It is a point where every possible escape starts disappearing at once. And the cruelest feature of that point is that it does not look like an ending. It looks like a continuation. One more kilometer, one more burn, one more reading, one more hour. The descent feels like progress right up until the moment it becomes irreversible. And by then, the only thing left to do is watch the universe through a closing lens and understand, finally, completely, what too close means. It means you are still outside the black hole, and it no longer matters